Uh, yes, we can start, Ruchi.
Hi, am I visible and audible?
Yes, Ruchi.
Okay, so good morning, everyone. Welcome to the technical session on ROS. So in this session, to start it, we have our principal investigator, Professor Kavi Arya. So, Kavi sir, over to you.
Thanks, Ruchi. Nice to see a good crowd here. My name is Kavi Arya. I'm a professor of computer science in the computer science department of IIT Bombay. And the team that you'll be hearing from today is part of a project that we have at IIT Bombay called e-Yantra, which is funded by the Ministry of Education. Now, it's been in existence for some time. Originally, it started as a project to train large numbers of students in robotics and embedded systems. We started in about 2009. And originally, I was the program coordinator of the distance education project at IIT Bombay, where we wanted to make good quality teaching available to many, many engineering students, because you know what all the problems are. And from that experience, from trying to teach embedded systems through the distance education program, that means trying to teach embedded systems, a very practical subject where unless you've built something and things move and lights flash and so on, you've not really convinced yourself that you know very much. When I first tried to teach this online through the distance education project, it was an utter failure. From that failure in 2002, it was, right? We came up with a remarkable way of training people online in practical engineering skills. And later on, we got it funded by the ministry, and we tried to first train a lot of teachers in this, thinking that if we train the teachers, then it'll cause a revolution and teachers will train lots of students and so on. We trained 700 teachers in a 3-day residential workshop at IIT Bombay over 2 years, but nothing happened. Then we thought that maybe we need to do something else, because we have this remarkable stuff, this knowledge which we want to share with young people. It'll make them employable, it'll make them, charged, and help them enjoy engineering. And then we said, that, okay, let's go directly through the internet to the students. And what is it that students like to do? They like competitions. So we packaged our training as a competition where we train you, right? And then we make you compete. And ever since then, we've never looked back. So this paradigm has been in existence since 2012. We've been training large number of students online in hardcore engineering skills, as a result of which they are getting placed in very good companies like Shruti Joshi a couple of years ago. Typical example, she did ECE at IIT Lucknow. And then after her e-Yantra experience, she went and joined Amazon India. And after that, 1 year later, she was in Google India. And students who want to do higher degrees, postgraduate degrees, either MTechs in India or MS in the US or wherever you want, we've been finding our alumni getting to the top engineering schools like Carnegie Mellon and Stanford and Cornell, all these kind of places, and also the IIT system. Most of the e-Yantra staff who you're talking to have come to us through the competition. And after that, they do a few years with us as a project staff, and then they can have the option of doing an MTech or a PhD. So almost half our staff are registered for academic degrees. Even Rishi, the young man that you'll be speaking to today, is registered to do a master's in Canada very soon. So that's who we are. Our goal is to train large numbers of young people in India to render them relevant and useful to society. And the goal is to do it through project-based learning. And you'll get a little jhalak of what we are doing in this morning's session. And I'd also like you to know, and it'll be repeated later on, that the registrations for the e-Yantra competition this year are starting on the 1st of August. That means on Monday. And I would suggest that anybody who's interested in digging deeper into these topics, because we train you and cover all these things like ROS and image processing and machine learning and control system design, all these cool kind of stuff, which you kind of hear or read about it in books, but you actually don't do at college. We actually make you do it in a very practical way. And increasingly over COVID, we've been focusing on training students through a simulator first, and then if they're good enough, we take them onto the real hardware. So that's what we do. And for this, a very foundational skill is the robotic operating system, the open source operating system called ROS. And our entire training program on robots runs around ROS. So I'm delighted that you've sought fit to join us this morning. And I'd like to welcome you all and hand over the floor to Rishi, who will be speaking to you this morning. So Rishi, do you want to introduce yourself and then start? I'll bow out. Any questions here? Not at the moment. So Rishi, I'll hand the floor over to you. You can start.
Hi, good morning everyone. Namaste, I'm Rishi. I've been working here in e-Yantra as a theme developer for the past 4 years, and we've been teaching ROS all this time. And we've seen a huge impact it has on the community. So we go to like robotics meetups with like a lot of startups and say like to be honest, like many of the founders there, they credit e-Yantra for having introduced them to ROS basically. And no joke, all right. So and so we're proud to have a huge impact on the robotics community here in India, and we'd like to continue having this impact, so that's why we organize such sessions, so that we can expose just a appetizer sort of thing to what this field is about and what typical robotics developers, robotics engineers do. And then if you find yourself interested, how best to go about learning this stuff. So the plan for today in this quick session will be, I'll first give you an overview of robotics. Then Sahil and Simran will take over and they'll give you an overview of ROS basically. So I'll cover more of the conceptual and not theoretical, but the conceptual basis that underline our field basically. And then we'll carry on towards ROS from there, and I'll take about 20 minutes maximum, I guess. And yeah, then we'll move on to the real the topic of the session today, which is ROS. So I hope I'm clearly audible and visible. So hi, welcome everyone. And so quick note there, all of my images for today are used for like descriptive purposes, and we've taken them off of the internet. I'll just cite the sources as we go along. So we've seen robots all around. Robots have been in our collective imagination for the past, I'd say, 100 years now, basically. So when people, this image, this GIF you see of a robot waving hi to you, this comes up when you just Google robot, and go to the images section. So in our collective imaginations, and most of the images are like this, so in our collective imaginations, robots are like this, humanoid forms, floating even maybe, who ease our life for us, so humans have been toiling around for like 5 lakh years on this planet, people like you and me. But finally we have the technology and the knowledge in our hands to get rid of this toil, and that's what captivates people, and that's why most robotics engineers get into this field, so like you want to reduce the mehnat in this world, the senseless mazuri basically, which is senseless toil. I'll stick to English for this session. And this is what robots are in the collective imagination: sentient, sort of semi-sentient beings who make your life easier. But when you look at this weird looking car, it's a silhouette of Google's self-driving car. So like most of you here in this room are engineers basically. So we know that future of that hovering robot waving hi is not in the immediate future, right? Maybe not in the next 10 years. Hopefully in the next 50, we see these being ubiquitous. But yeah, you and me, as people in the technical field, as engineers, we are much more certain about other things like self-driving cars, which are also types of robot which do cool stuff autonomously. But yeah, for us, this is more of a less longer term goal. But you know what the reality is? Most robots in this world today, like overwhelming majority, like 95% of robots in the typical sense today, are industrial robots, which just do one task from A to B. They're programmed and they'll do just that. If you come in their way, they'll injure you. So they are not. They are not doted with intelligence. Let's say they just you program a task and they'll do it very well with the highest of quality and consistency, basically. So let's put all of these things on an axis. Let's introduce these axes X, Y, and Z, whatever. So on the horizontal one, you see the complexity of the system and its operating conditions, basically. So today we find ourselves, okay, why did this change? Okay, so today on this horizontal axis, we find ourselves with robots that have sufficient prior information of their surroundings and of their task. So this robot which puts a windshield on the car, maybe just before it, another robot comes and puts the epoxy resin that actually sticks the windshield to the car very accurately, and this guy just picks up the windshield with suction cups and puts it there. So it has all the prior information. The body of the car will always be precisely aligned, and everything is perfect in a controlled environment. And it is doing a single predefined task. If you look here on the vertical axis, which is the complexity of the task. So this is where we find ourselves today, and on the top right is where our goal is, basically. So that's where we want to get to. So getting there will involve, let's take the vertical axis first, for doing multiple predefined tasks. So instead of like one robot applying the epoxy and the other the windshield, maybe one person can do one robot can do both the tasks. But yeah, this is just a toy example. And then moving on to even more complex missions, so where you just instruct, okay, go make me a pasta or whatever, go make me a coffee. And finally, this will be very interactive and human-centered. So instead of just making your coffee in an industrial kitchen where everything is controlled, you can have the robot in your home and have it, just call it and tell it to get you coffee, essentially. And on the horizontal axis, yes, you have to move towards partially, unknown but still non-changing conditions in the short term, medium term, which is what self-driving cars are. So your roads, they don't change every day. Yeah, with the monsoons here in our country, yes, that is a different situation, but still the structure of the road and your destination, like where you want to go and how you reach there, is sort of non-changing. And then ultimately towards partially unknown and changing environments. So things like stuff in your house, like my house is sort of a mess. Things keep moving. Things are everywhere. No set relation. But yeah, like if a robot can operate in such conditions, that is the future we seek, basically. And this Z-axis, so to speak, this 3D axis, it's like single agent versus multiple agent systems, which is if multiple robots can collaborate together to achieve a certain task, that will be cool as well. So the building blocks of robotics are perception, planning, and control. So perception is just gathering data about what surrounds you, basically. So it could be in n number of ways, some of which I'll cover in the next slides. Planning is then deciding what to do with that data. And control is finally, moving your actuators, actually moving your muscles to, enact whatever decision you have taken, basically. So perception, it can be handled by cameras as well. Typically, this image you see from like a pedestrian walking with a camera, it could be a standard camera. And then now with the advent of like really large scale machine learning techniques like deep learning and so on, it has become extremely ubiquitous. This sort of thing where the learning algorithm predicts what things are when within a bounding box and a certain confidence. And then you see these images from like a very old Tesla firmware, the full self-driving thing. And these people, they use like high dynamic range cameras, so that even they can differentiate between the brighter and the darker regions as well, instead of like saturating stuff. You have this feature in your phones as well right now. So object detection and tracking using cameras, basically. So that's one more modality of perception, but this isn't just anything new. So ever since the 1950s, a lot of computation has been put behind perception. So back in like before World War II and so on, you had radar and so on, and they just pinpointed an object in the sky. So a lot of money and computational effort was put behind things like, okay, now if two airplanes cross each other, cross each other's paths, if you just have the dots, you still don't know which one is which, right? So you have to sort of do some planning and some sensor fusion, it's a technical word, to keep track of this airplane which was like heading in this direction and the other one which was heading in the other direction. And when they cross each other, you can still assign the proper tracks to them, and you don't know, and you're certain that they just haven't swapped positions and so on. So if you just track their positions, you might not be certain, right? So now if that plane has come here and taken a sharp right turn or whatever like that, stuff like that. So there are lots and lots of computation, and both theory and practical development has been put behind perception systems ever since the past 70 to 80 years, basically. And so this is an older example of a radar. And the same thing continues today, in a more advanced form. Images from Wikipedia, air traffic controllers. And now we have interesting systems like lidars, which can generate, which like throw off lasers, and just like your TV remote, which throws off a IR beam. This guy throws off a laser, and actually, just like radar, it receives it back as well. And from that, they can form 3D point clouds, basically, of what in a 3D volume, what regions are occupied and what are not, and then you can do the same sort of object detection and tracking from this data as well. So 3D point cloud creation and inference. So inference is a huge part of perception as well. And then this is also a modality of perception, which is just reading data off of an IMU, basically. So here you see a person with a drone chassis, twisting it around, and on the laptop screen, you see the equivalent movements that are being registered by the IMU, which is the inertial measurement unit, which consists of a gyroscope, a magnetometer, an accelerometer, and so on. So these are cool sensors. I'll not get into them right now. Then comes planning. So planning is, okay, now you want to go someplace. How do you get there? So this is a robotic arm, a UR5. Incidentally, we have one live hardware example in our lab, which we use for the EYRC themes. So yeah, if you're interested in working on mobile robotics arms, please do register. But yeah, now you want to move this arm from one position to the other, and it has like 7 joints, right? So how do you determine the sequence of what joint should move how much, how fast, and so on, and when, basically? So that is the domain of planning, basically. So there's a lot of different planning algorithms. This is motion planning for manipulators. This example here you see is a sort of randomized tree graph, basically, rapidly exploring random trees, they are called. Typically this class of algorithms, which, for a mobile robot, if it wants to get from A to B, and if it knows its environment, then it can create a optimal sort of path through that environment, avoiding the obstacles and so on. And then comes control, so now you want to decide that in this case, in this image which you see here, that you want to do a flip, how do you actually do it? So you command the motors with like certain torques and velocities and angles again. And so these are the MIT's mini cheetah robots, pretty cool ones, low cost as well. So yeah, so this is the domain of control. So, in commanding your actuators properly, and, taking into consideration their parameters as well. So this is what an actuator typically consists of. That the robot which you saw, the mini cheetah, it has like 10 of these motors essentially, and it's not just a electromechanical aspect of these motors and motor control and magnets, but also a lot of electronics and software involved as well to actually control these things, because these things are commutated electronically. So it's the tiniest of movements that this motor makes. There's actually a bunch of MOSFETs turning on and off very rapidly, controlled by a microcontroller, commanding these things what to do at a very high rate, basically, like on the order of megahertz even. So yes, this is the actual controller board. You'll see a lot of MOSFETs, a lot of capacitors, and on the other side, you'll see a microcontroller as well. So yeah. So moving on to some theoretical underpinnings, so one great thing about our fields of robotics is that it involves theoretical underpinnings from a whole wide range of applications. So everything from control systems to image processing, computer vision to now machine learning, and at the very core of it, math basically, and software practices like in software development. So yes, Arjun, our colleague here, made a nice graph for us today. So so for robotics, all of these components are involved. Okay. So you have to decide what power sources you have to use, volt, batteries, and so on. That's a huge consideration in itself. The actuators, again, a huge field in itself. You can do a bachelor's in engineering in each of these fields, by themselves. So yeah, like sensing, manipulation, locomotion, which is like moving around, and environmental interaction and navigation. And then one great field also is like human robot interaction, human machine interaction, it's also called. So like, and then finally control and industrial design, which is very important. So yeah, HMI is also, so if you're not, maybe if you're more of the designer sort and more of the thinking philosophical sort, you might like industrial design and HMI basically. So yeah, a lot of thought goes into using all of the software which we use daily, and this is the same case for robots as well basically. So this nice map made by Brian Douglas, a very popular and nice YouTuber, basically. Just to give you an example of what lies like. So each of the points listed in the previous slide, they are a domain by themselves. You can have an entire career in just one of those domains. So we are very lucky to be exposed to a lot of them. So I read once that a good engineer should be like a banyan tree, so it spreads far and wide, its branches spread far and wide, so you have domain knowledge in a whole lot of domains, but at the same time your roots go very deep as well basically. So which is that you have deep expertise in one domain of knowledge at the same time. So just this illustrative slide is just to showcase that each of the slide points that you saw in the previous slide, that those are domains in themselves to be respected, and if you're interested, by all means explore them and become an expert in any one of them basically. So the same is the case with mathematics, which is sort of the underlying basis of all of this. So mathematics has a lot of applications. So even if you don't feel interested in math and feel like in college math courses are pointless and so on, I'd say that please be aware of the ramifications of that. They might not be always conveyed to you basically, of how useful whatever skills you're learning are, but trust me, do explore where these skills are actually used. That will give you a lot of interest in actually mastering math, which is extremely critical in our domain basically. So those were the theoretical underpinnings, but at the same time we have a lot of tools and so a typical robotics developer or any software developer, for instance, has to deal with the entire pipeline of tools, So that is where ROS comes in, to merge all of these together and make your life easier. But yeah, at the same time, so just in our themes, we use all of these tools. So at the same time, when you're getting into the field, it is, and if you have like no prior inclination or experience, it is definitely a bit overwhelming to get started with all of these different tools. And so Python is at the core, Python and C++. But yeah, when you're starting out, maybe you're better to stick with Python, I guess. And the second most important thing is Linux. So Linux is everywhere. It's your Android phones, the servers we are using right now are running on Linux. Even YouTube, if you're seeing this on YouTube, it's running on Linux. So and the pipeline, the way it's set up, makes it very conducive for robotics tasks. So essentially, Python and Linux are your core things. Then on top of that, we use simulators like Gazebo, and then for creating different robots and their arenas, we use 3D creation tools like Blender. So this Tux is like the symbol of Linux, basically. Tux is the penguin's name. So it looks like a tuxedo, with the black and white thing. Then for drones, we use PX4, and for simulating our robots, we use Gazebo and RViz. A lot of perception is involved in our themes as well, which is mostly handled by OpenCV. And then to merge all of these things together, we use ROS. So here, this is the end of my presentation. I'd like to hand over to Sahil or Simranjit to, actually get you excited about ROS and, why you should learn it, basically. So thank you. And yeah, if you have any questions, you can ask them in chat, maybe. And for the continuity of the session, I'll directly hand it over to Sahil or Simranjit. Yeah. Thank you for listening.
Thank you, Rishi. Okay, so Arjun, any comment from you, and then I will start. If you have any question, please ask right now. So then we'll start with the next presentation that will be more focused on the ROS. So we'll discuss like why all this ROS is important, and Rishi has already gives you a glimpse of like how complex robotics is, and each one of us has different expertise. Like some of us are from computer science background, some of us are like from electronics, mechanical and all, and robotics actually involves all of this. So how we can integrate all our expertise in single domain, that is what our goal is here, like to introducing you to the ROS. And yeah, so I'll start with the presentation, but in the meantime, if Rishi and Arjun, if you want to make some comments, please go ahead.
I just wanted to add quickly about that slide about the theoretical underpinnings. There's we wanted to highlight the fact that in robotics, when we do it in BTech, at least in hobby grade robotics, you might get away with not connecting the dots between what is going on in BTech and what we are doing in the project. But if you want to take that robotics level to a higher level, doing things that are world class or even the best robots that you can build, then you will have to eventually connect all the dots between what you did in BTech. That is all of this stuff that you see on the map of mathematics or the map of control systems or the map of any other thing that was shown in the previous slide. If you connect those dots with what you're doing in the project and use all that theory that you study in the class, that is, I think, when the project goes to a whole new level. And that is what I'm trying to do right now in the field of controls. And just a message for you guys. So if you start in the BTech itself, that'll be even better. So yeah, that's all. Thanks.
Okay, thank you, Arjun. So shall we start with our next presentation? Or I guess there are a few questions in the chat. No? Okay. It's just the appreciation. Okay. I hope my screen is visible.
Yes.
Yes.
Okay. So welcome again, everyone. I'm Simranjit Singh. I'm working with e-Yantra and also doing my PhD in electrical department in IIT Bombay. So my work is basically focused on high performance computing. Sorry?
So if they could do it, then
Hello?
definitely students also can do that. And that's how we
Someone is speaking in audience or... Okay, all right, I guess. Yeah, okay. So my area of expertise is in high performance computing. I look into how we can accelerate our computing, like image processing or machine learning algorithm using FPGAs and like neuromorphic computing and all. So our objective today is my screen visible now?
Yes, it is visible.
Yes.
You can see like introduction to ROS slide, right?
Yes.
Okay, cool. So so our objective today for this technical session is like just to introduce the concept of ROS. We just want to emphasize like why this skill is really important in today's generation, why you should actually learn these concepts and how complex this robotics problem is. So we are actually using this from last 5 years in eYantra, and we also run few themes just focusing on this ROS, because we see like, because this robot operating system and this ROS is actually the future, because we can it's very modular and we can combine others expertise to implement some complex problem. So I'll just give you the introduction to ROS. What is ROS? Why we need ROS? And some basic like installation, not the installation, but what are the basic commands and what we can do with the ROS. Okay, so this is like the sort of table of content for this presentation. First, we'll discuss about, okay, what is robot operating system and why we need this, and some levels of abstraction in ROS. Then later we discuss, okay, what are the basic commands in ROS, how we can create our package, and few uh, examples on how we can run the code and all. And at the end, Sahil will take over on this, like what are the different tools in ROS and simulator and the hardware. And in the end, we'll also discuss, okay, what we are doing in this particular field. Okay, so in the meantime, in the presentation, if you have any question, just interrupt me and ask the question. It will be better to handle the question at that particular slide. So I already have slide number. Just mark the slide number and just point it out where you have any questions. Okay, so let's start with the ROS. So ROS, as the name is, like robot operating system. It's a open source, easy to use framework that is basically used to write the software for robots. Like the normally we have operating system for our system like Windows and Linux. This is similar to write the framework for robotic application. So this platform has numbers of tools and library to solve complex problems. So we can integrate more number of libraries, and we can just treat them as a black box. In case we want to modify, we can also, but if that is not our area of expert, we can just integrate that in our sort of application and we can use it. So the advantage of this ROS is we can decide, okay, how much we want to use the ROS to solve the problem. We can start from the basic, like we can let's say if you want to build some line following board, you can also use the ROS, and even do some complex problem like self-driving car, as Rishi mentioned in earlier presentation slides. If you want to build some self-driving cars, it includes so many aspects of engineering. So you can solve that sort of problem as well in the ROS. So along with this libraries and tool, it's also provides some simulation and visualization tool that help us to debug our algorithm and the code. And even before going to the hardware, we can test our algorithms in the simulation, like how my algorithm will behave if I put it this algorithm on the hardware. So this ROS actually provide all those facilities to use that. So we can debug our algorithms. And as I mentioned, like we can also use it very extensively or minimal according to our application requirement. And we can also develop our own packages and all. And that we will discuss, like what are the different commands to use that. So the next question is why ROS? Because there are so many libraries and other sort of stuff. Why we want to use this sort of like ROS system? So the first advantage I see is it's a very open source framework. I'm big fan of open source. Like whatever I develop, mainly try to open source or maybe to commercialize as well. But yeah, so on the side of open source. Let's consider if I am expert in some high performance computing and I use the ROS. I can open source my code to you. You can take a look, and then you can add new feature to that particular code and open source it again. So it's more like a community there. It's like keep on evolving to make it more generic and sort of like complex algorithm, so that more expertise are there to handle all those codes. Okay, so that gives more flexibility to the users. Like um, in my case, okay, if I say I have expertise in HPC, there are number of people who have expertise in HPC. If they are like open source, you can choose, okay, I don't want to use Simranjit's code. I want to use someone else's code, and it's a flexibility. You can decide which one you want to use. And the next advantage, as I already mentioned, it's provide the simulation tools, and without any hardware implementation, because we know, like, if we get into the field of robotics, hardware and all, it's very expensive, right? Like, to buy a sensor or this lidar, they are really expensive sensors. So, but we have the access to tool like, sorry, hello, I'm hearing something else. I can still hear someone.
Just a second, so let's move to
Yeah. Please mute yourself. I guess it's something is running on YouTube or something like that, I guess.
Yeah, it's
Yeah,
fine.
okay.
now it's
Yeah, okay. Okay, so my point here is, like, we can run complex algorithm without having hardware in our hand, and we can use the simulation. We can design any sort of like complex robot model in the simulation, and we can run our algorithm to perform some application in the simulation itself. And it's also support major programming languages like Python and C++. So we don't need to worry about, because if you run some application on C++, you have to build that application. You have to add few paths, environment variables, where your object file is and where your binary file is, to handle all those things. So in ROS, there is a dedicated workspace for ROS, where you don't need to worry about this CMake paths, environment paths, and all those variables. It take care of all those, and it's also support Python. I guess we are more familiar with Python and all nowadays, and we can write our ROS infrastructure in the Python itself to test to test our algorithms. And it also has a very best customer support, like ROS forums and well documented uh, like tutorials and all. I won't say well documented, but yeah, a little bit documentations are there. But yes, you can get into the tutorials and get a feel like how the rows and everything is working and all. Okay, so it also support variety of robots and sensors already. So you can just go on the ROS simulator, and you can download few open source models, and you can integrate those in simulator, and you can start working on this. Like, these are few examples, like in case you want to explore something in what do you call, like, underwater something, or drone based application, humanoid and all. You can just import all these models into your simulation, and you can start working on this. So that's the sort of advantage here to using ROS. So uh, now I'll start introducing, okay, why ROS is important, and what are the different command to use ROS, how we can initiate it, and how we can install it. I'll just give you one example. Like, let's say this is one robot from NASA, and if we look at this, what are the different concept you look like uh, to move from one position to another, and how complex this is, because to handle this sort of robotic application, we need arm manipulation. So this is a very different field from vision, actually, because it's need a how we can as Rishi mentioned, like how we can design the plan or for the robotic arm, and then navigation concept is there, communication is there. These are like dedicated field. So if there in this case, if we take example of NASA, how they will be developing this sort of application, there will be different team who will be working on arm manipulation, a separate team working on just on the vision, and another team for navigation, another team for communication. But to run this sort of application, we need to combine all these application into a one, and then this robot will work, right? So this ROS actually give us this modularity. We can take it this arm manipulation from somewhere, vision algorithm from somewhere, navigation from somewhere, communication algorithms from somewhere, and we can combine it and make a single application. So that is the modularity of ROS. We can choose different expertise and we can combine them and run our application. I guess my point is clear to everyone, right? If you have any doubt, just ask in a chat, or you can unmute yourself and ask. Okay. Okay, let's move to ROS infrastructure. How ROS actually handle all these, like what is the like the bare one of this ROS infrastructure? It's actually based on publisher and subscriber model for messages passing, and we can also record and play a few messages. In case you have some sensor, you can record that sensor data and you can pass it to your friend or to someone who is actually working on that data, and you can play again that those messages and use it. And it's also request response service for same to pass the messages. I will discuss in little detail about what this publisher, subscriber, and this node and ROS Bag is. And as I already mentioned, like we can use Python and C++ for ROS communication, and we can write some executable on this for ROS actually, so that we can integrate them and we can work, we can design some application on it. Okay. So this is the level of abstraction in ROS. So the first point to learn in ROS is like the ROS master. It's actually a naming and registration service. So how we initiate ROS in our system is, that is the ROS master. We run one command called ROS core. So that initiate a ROS core inside our system. That so when we run this ROS command, it will be looking for if there is any module who want to pass a message to someone. So it will keep looking until there is a match. It will track the publisher and subscriber, and then it will connect. Okay, if I let's say if there is a code, we are doing some image processing, and there are two codes who is just capturing the image from the camera, and another is doing some perception algorithm on it. So these are two different codes. So when perception algorithm is running, it need camera as a input, right? So camera input is another code. So when we run the ROS master, it will keep checking, okay, my vision or my perception algorithm need camera as a input. Whenever there is a camera input, it will connect both of them, camera and the perception algorithm, and then it will bypass them. Like they can communicate each other, and ROS will sit aside and keep looking if there any other publisher or subscriber in the network. Okay. So node, then another concept is node. These are the executable, like in C++, how we when we try to build something, then there is one object file, right? So these node are like that. These are like the basic codes. When we build something, it will create one file, that is the executable file, under which topic and service are communicating. So in each file, there will be only a single node, but there will be multiple topics and service under that particular node. So you can consider it like if I have a one Python script. In that Python script, there will be one node, but there can be multiple topic and services. So topic and services, those are like how we transmit the data. So these are like buses. They will carry the data from one position to another. Like if there are publisher and subscriber, they'll carry the data and pass to the subscriber. And how the topic actually handle this data, that is called the messages. So messages is like a data structure on which we can in that particular data structure, we format the data, we can send to the topic, and node will handle how where I have to connect, where this message needs to be passed. So these are the few level of abstraction in ROS. We'll in every Python script we should have this like nodes, topic and messages to pass or interchange the data in between. Okay, so we can design publisher and subscriber, but to design that, we obviously need a name of node on which then we'll decide the topic on which we actually want to pass the data, and then the data structure in which format we want to pass the data. But we can also design our custom messages as well, but there are a few standard messages as well, like int16 and some image format. These are few messages, those they already exist. We can fit our image data into, or like in this case, if we want to pass some image, we can fit our image data into the sensor messages and the image messages, and we can pass it to the topic for some other computation. Okay, so these are few commands to run or handle this ROS scenario. So first command we call is ROS core, as is the name is the ROS core. It's run the basic core of the ROS, that is like the ROS master. So to communicate anything in the ROS, need we first need master, which can connect to publisher and subscriber. Then only communication can be initiated. So this is the first command. Then to check the rows, like the node, what are the nodes in my network, because the ROS infrastructure is basically a network. So where we can connect different aspects, and we can set up a communication between them, and then we'll start exchanging their messages in form of some data structure, and they can perform the task. So ROS core is actually to setting up the network, initialization of the network, and then we can run other commands like our node and topics to pass or exchange the information. So ROS node is actually to identify what are the different node in my network. We can check, okay, then further it's divided like ROS node list. It's like the list all the live nodes in the network. What are the different nodes? These are like few debugging skills. Like if there is a large network, we want to understand how things are connected with each other, right? So we can check and list what are the different active nodes in the network, and then we can also find the information of that particular node. To find the information of that particular node, we pass a command called ROS node info, and then the name of that node, because there can be multiple nodes in the network. So let's say some node is running called ABC, and then another node is PQR. You want to check the information, how many subscriber or the publishers are there in that particular node. You can just pass a command ROS node info and the name of that node, let's say ABC. So that will give us the detail, okay, how many number of publishers are there in that particular node, how many subscribers are there, what are the data format of those topics and the messages and all. And other commands are, these are two very important commands just to get the information and all. These are very rare to use, but you should know, like, okay, what are these commands. So ROS node kill is again to kill that particular node. It will remove that particular node in from the network. And then another command is ROS node ping, that will show us the connectivity of that particular node. So in all these commands, after this ROS node list, we have to pass the name of that particular node about which we actually want to see some information about. So we'll pass this command ROS node info node, and then we can see the particular information about it, right? Similarly, this is one command ROS cd. This is like the similar command we have in our Linux system called change directory, but in this case is the ROS change directory. It will keep switching between not keep switching, you can pass the package name after this command, like ROS cd. You want to move some package called abc, it will directly change the directory to that particular package. Okay, so then another very important command is called ROS topic. It's similar to the ROS node, but that this is more focused on the side of topics. So similar to ROS node list, if we run this command ROS topic list, it will list all the active topics in the network. And then we can also check the information by passing the name of that particular topic, and it will show us like how this topic is connected, what is the data structure of this particular topic, and who is actually publishing or subscribing this topic. So you can check all the information about that particular topic. And then if you want to see what is the information in that particular topic, you can also run a command called ROS topic echo, and then the name of that particular topic, and then it will start printing the data published in that given topic. So you can just for the debugging purpose, you can see, okay, if what is the information in that topic, if is publisher is still publishing some information or on that particular topic or not. And again, you can also pass some information to that particular topic. So to publish some information on that topic, like in this command, like ROS topic echo, I guess my cursor is visible, right? So in this command, like ROS topic echo, we are seeing some information on our screen, right? So someone is publishing that information, and then only we can print it and see, right? So in this another last command called ROS topic pub, this is to publish the information. So how we can publish some information on that particular topic, that is like ROS topic pub, just pub, and then the name of that topic, and then we have to form the data structure, and we have to pass that data. So when we run this command, it will start publishing this data on that particular topic that we have mentioned in this command. Okay, so in this way we can pass the information, publish it, and then on the other side we can also subscribe it. Subscribe is basically echoing, give a echo to that particular topic, right? We can also write it in our script. All these commands we can write it in script and perform a very long sort of algorithm based on this. And this is command like how to run some code. So to run some code in a ROS, we use this ROS run command. Then we'll pass the name of that package, and then the script. In this case of, like, if you want to run some executable node that is in Python, we'll pass the name of that package, ROS run name of that package, and the name of that Python script. And it will start publishing that data in a ROS network. And we can also combine multiple nodes into a single file that is called launch file. And let's say if in our case we have 100 of scripts to handle some application, we can write all the scripts in a one single file that is called launch file, and we can run all the executable file, all our nodes at a single run. So that command is called ROS launch. It's similar to ROS run, but this will run multiple executable nodes. So we can pass ROS launch and then the name of that particular package where our launch file is, and then the name of that launch file. It will start executing those files. Now I'll discuss about how we can create some package in ROS. So if you remember in earlier slide, I mentioned like ROS actually handle all those path variables if you are implementing some C++ or Python scripts. So there is dedicated workspace for ROS. It's called Catkin workspace. It's CMake based build system in ROS, and all the packages that are in ROS, we have to put all those packages in the Catkin workspace. Then we can source it, and it will be visible in our ROS structure. Then we can run it using all those commands like ROS node, ROS run, ROS launch, and then we can execute it them, and they will be visible in our network. So if we look what is inside this ROS workspace or the ROS package, there are few files like which we have to modify to make it compatible with ROS. So sorry. So the first file is called cmakelist.txt file. This actually contains the executable dependency library required to build the package. One template is already there actually in cmake.list text file, we just have to add the name of our script that we want to execute, right? So then when we execute the Catkin workspace, it will build that particular node and create a object file for that. Okay. And then it's like package.xml file. It's actually the contains authorship and maintainer and all those other build and run dependency. But this is not very important file, but this one is cmake.txt file is important if you are writing anything in C++. But if you are writing anything in Python, then we don't need to modify these two these two files. And next is like src folder. This is like the source folder which contain all our source code, so that ROS package can find that particular code and execute that. Then there are a few other files. We can also create another folders in the workspace. That's not a big deal. And there are a few folders called include and scripts, which contains header files and Python scripts. I normally create one folder called script and put all my Python script in that. And if you know, like, in the Python we don't need to build anything, right? So Python is already an executable. We can directly run that, so we don't need to run Catkin workspace and all. But to make sure it's visible in our network, we have to source the network so that it can identify what sort of packages are there, so that we can run it using the commands. Otherwise we can directly run Python and the name of that script, that those node will also be visible in our network. Okay, so this is just a very simple example of it's called TurtleSim. That code is already there in ROS. If someone has already installed the ROS, they can type this command called ROS run TurtleSim. So in this command, this is command to run some executable, right? And then TurtleSim is the name of this package, and TurtleSim underscore node is node inside this TurtleSim package. So this is the example how we run a code in the ROS. Yes.
So package is like a library, right? Then.
Yeah, package is like a number of inside the package. There can be multiple nodes, multiple launch scripts, or yeah. So when you pass, like, let's say this is a command, right? ROS run TurtleSim. Then inside this TurtleSim, we are like, okay, we are pointing to this particular package, and inside that package there can be multiple nodes like TurtleSim underscore node, TurtleSim, or maybe ABC node, PQR, any number of nodes. But this is just to point out, okay, what we actually want to execute. Okay, so in this command, if we run this command, so this TurtleSim package is already there in the ROS basic installation, and then we can run this TurtleSim dot node. That will show us one GUI with one turtle. Some turtle is there, right? So this sort of turtle. But this is just a single command to open this GUI. If we want to move this turtle from A to B point, we can also write a script, or we can, let's say we want to control it through our keyboard, right? To make it control from our keyboard, we have to run something else that is called tally operations. So you can install that package, you can make some modification. First we have to identify, if I want to move this robot from one point to B point, what sort of messages I need so that it can move from one point to another. So there are few parameters called like velocity we need, or we need angular momentum or angular velocity, right? These are few parameters that are needed to make it to move from one position to another. So we have to identify, okay, this is the data structure, and this is the name of this topic, and then you can pass some information to that topic, and this turtle will move from one position to another. Okay, so even you can write the script, identify, okay, what are the in case, like, if we are running this command, let's say ROS run TurtleSim node, and we want to see, okay, what are the different topics under this command, then we can run in a separate terminal. We don't have to close it, obviously. In the another terminal, we can run another command called ROS topic list. So that will list, okay, what are the different topics in TurtleSim underscore node. And then if you look at the information of that topic, I guess there will be one topic called CMD well, if I remember correctly. And then you can check the information using ROS topic info and then the name of that topic, CMD well. And that will show us, okay, what is the data structure of that particular topic. That will be like a linear XYZ and then the angular XYZ. And then in case we want to move this turtle from one position to another in another terminal or in the same terminal, we can pass the command ROS run or not ROS topic pub and then the name of the topic on which we want to pass the information, and then we can change those value. A linear XYZ and angular XYZ, the turtle will move in that given data according to that given data. Okay, so when one this is like the first sort of like introduction to the ROS. This is the first example also in the ROS wiki if you go. So this is like the starting point. You can install ROS on your system and try to play around these packages and the simulation and all. Okay. So next is like there are different tools in the ROS as Rishi also mentioned, I also mentioned, like we have simulation and visualization tools. Those can be used to debug our algorithms. So I'll hand over the floor to Sahil. He will cover these topics related to ROS tools. If you have any questions, you can ask right now.
There will be a small demonstration, right? For that TurtleSim or something.
So which is the more preferred
We-
language for write up?
We normally use Python because it's there are number of libraries in Python that we can integrate, and it's also depend upon the application. If you are looking for some high speed or timing is the major concern, then obviously we write in C++. But for the beginners or the starting point, I would recommend go ahead with Python.
Thank you, sir.
Yeah. Anything else? Okay. Sahil, over to you. Do you want me to keep presenting my screen or you want to present?
Yeah, it's better to present. Like I can tell you when to move slides.
Okay, you want to present?
No, you
Or
can
is it
present,
okay?
like, you can keep the slides.
Okay, cool. Okay, go ahead.
Thank you, Simranjit. So till now we have discussed files. It's like a project. So you do various projects, and inside projects you may have various files. So package is a collection of files. So further we go. So we have ROS tools. So there are various ROS packages developed by the open source communities, which you can use as a tool for your any ROS project. So one of the ROS tool is 3D visualization tool, which is RViz, ROS visualization tool. So it is basically a 3D graphical visualization tool, uh, which you can interface with any of your simulator or a hardware. It can even be a hardware robot. So which we can visualize it in the RViz. You can also visualize the various sensors, like whatever data you are getting from the sensors. Let's say you have a LiDAR. So I hope you all know what is LiDAR. So LiDAR is basically a sensor which you can scan the entire area and you can get the distance of the entire area. So it's basically used in the self-driving cars, most specifically. It has various applications also. So like LiDAR is one of the sensors. You have various sensors, ultrasonic sensors, or any the camera is also a sensor. So you can get the data in the ROS and you can visualize it in the RViz. So like you can, let's say you're getting a data from an image. So you can visualize that image in the RViz screen. So in the RViz screen, you can visualize the sensors data. And also you can visualize the motion of your robot. Let's say my bot is moving forward. So that thing you can visualize in the RViz tool. So it has various applications. So it can be used for perception in computer vision application where you want to visualize something. Let's say you want to have a depth point cloud data. So depth point cloud data is a 3D camera data that you are getting. So we have various depth sensors from which you can get 3D data of an object, like you get only a XY in a image, in a 2D image. So you get a 3D depth of image of an object, distance, like you can also get a distance as image from the depth camera. And you can use it for navigation application, you can use it for manipulation application. Yeah, so there are various applications for it. Next slide, Manju. Yeah, so this is how your RViz screen looks like. You have a left panel, right panel, some toolbars at the top and the bottom. So this is the bot. So in the center, you see a bot that we actually have. So this is actual hardware that we have in our lab at ERTS lab, e-Yantra lab. So you see here the mobile base and a UR5 robotic arm, which is the industrial standard robotic arm, with a gripper and few sensors attached to it. So you can get this robot model visualized in the RViz. You can get this panel as per your need. You can also get various sensor data. To the left side, you can see the various options. You can select various ROS topics. So as you know, whatever data we are getting, it is the form of ROS topics. So you can get all the data, visualize all the ROS topic data and visualize it here in the RViz screen. Let's say the sensor data, like say the LiDAR or the camera data, you can visualize here in the RViz screen. Also, you can visualize the motion here. So in the center, you will see the motion of the object, robot or like any other thing. And you can select various topics. You can add to various topics. So also this RViz screen is most useful. Like it has various uses. Like it can also be useful for the manipulation operator. Like there is a manipulation package named MoveIt. So if you explore further, you will know what is MoveIt is. So MoveIt is basically industrial standard. It's a ROS package for industrial standard robotic arm and any other robotic arm you can use. So it uses RViz to visualize all the manipulation motions, also various algorithms, and that all you can apply in the movement. Yeah, so that was the ROS visualization. So next is RQT plot. So let's say I want to plot the ROS topic data. Let's say I want to tune my PID controller, any other controller. But let's say I want to have visualize any time series data. So that I can visualize using RQT plot. So it is a 2D plot tool that is, it's a package basically. So RQT plot is a package developed by the ROS community. So you can visualize various data, time series data here. And also you can customize as per your need. You can add many, whatever data you want to add in the graph, you can visualize it here in the RQT plot. Yeah. Next. Yeah, next is a very important tool named as RQT graph. So this is the most important tool when you want to debug something. Like let's say you have created various ROS nodes, various ROS topics, and you want to find out which topic is being communicated and where communication is not happening. So this is an important tool. So this visualization tool gives you all the running processes that's happening in the ROS. So here you see various nodes. So slash joint state publisher is one of the node, joint state publisher. There are various nodes and there are a few topics. Joint states is a topic. So you can see how your data is being communicated here in the using the RQT graph. So this is the most important tool when you want to debug in ROS ecosystem. Yeah, next slide. Yeah, ROS Bag. Next is ROS Bag. So ROS Bag is an important command line tool for recording and playing back messages into a bag file. So what ROS Bag is, it basically stores the data of all the, suppose let's say I want to store data of particular topic or all the topics. So let's say I want to get collect data of all the ROS topics, whatever data is getting sent from one node to the other node, the ROS topics. So you can save all the ROS topics inside the ROS Bag. So this is a very important file because let's say you want to do certain deep learning application. Let's say you want to train a model. So you want data for that. So what you can do is you can use ROS Bag to collect data from the sensors. You can store it in the ROS Bag and then you can use that data to play and train your model. Like let's say you can collect all the images and you can use that collected data for your application. So next application is you can record all the ROS Bag data. Let's say all my simulator sensors, motions, all that. And you can record and play it afterwards in the ROS Gazebo environment, in the ROS environment. Gazebo I will cover later. What Gazebo is. So it basically saves all the specified topics and messages in a file. So you can play it afterwards after once the data has been collected. Yeah. Next is simulator and hardware. So ROS has very integrations with various simulators. So integrations with simulators like Gazebo. So Gazebo is the most important simulator, which ROS has very good compatibility with. It also has compatibility with simulators like TurtleSim, Carla simulator. So Carla is a self-driving simulator. It has lately it is also had support with Unity. Like Unity, you all will know that's a gaming gaming. You need Unity to create a games, right? So ROS has also extended support to Unity. So there are various other simulators where you can find support for ROS. So most important simulator is the Gazebo, which is like very good compatibility with ROS. And ROS is also compatible with various hardwares. Like you can have ROS installed in the PLCs, robot controllers, servos, IO networks, etc. It has also support for single board computer. Like Raspberry Pi is the most famous single board computer. It has support for NVIDIA boards, micro. So recently they have also extended support for microcontrollers. So there is something called as micro ROS, where you can do some activities with ROS for microcontrollers. And yeah, you can also have in the PC. You can use ROS in your system. So yeah, that's what they support. And next is the simulator. So Gazebo is a simulator which has a great compatibility with ROS. It's an open source 3D robotics simulator. It supports various physics engines like ODE, Bullet, SimBody, and Dart. So ODE is the default physics engine. You can change as per your need in the Gazebo simulator. So it's a 3D simulator. You can create a robot, any robot model from scratch and use it in the Gazebo simulator. You can develop any custom plugins. So plugins are basically C++ scripts for creating your own custom sensors and any actuation you need in the simulator. It's like physics script that whatever you want to do in the simulator in the simulator. So simulator, you can create a very real world. Like you can even control the wind, atmosphere, and various other parameters inside the simulator. It has support for various sensors. So it has various sensors which has been given by the Gazebo environment, Gazebo community there. So you can have sensors for cameras, depth camera, and various other sensors. So and various other actuators also. So it has a very good integration with ROS. Slide. Yeah, so this is how the Gazebo window looks like. So this is the very default Gazebo window, and we have added our eBot here. So eBot is a robot, the actual robot model we have in the lab. So this model we have here. So you can add here any robot model here. So in the center you see is the main scene of the Gazebo window. So this is called a main scene of the Gazebo window where your robot will be spawned, or you can change your world. So you can customize your world. So right now it's a basic Gazebo world with tiles you see on the ground. So you can add any world, like you can add forest, let's say any water world, any world you can add here, buildings, etc. So on the left side, you see a panel where you can add various, you can see various world files. So what world files are basically the files that are added in the background of the, like in the scene. So robot model is the main thing which will actuate in the Gazebo environment, and a world file is like the static object which will be seen in the Gazebo simulator. So it can be a greenhouse environment. So that's the world file. Next is import. So you can no, on the same simulator. Yeah, you can import various models here in the environment. Like you can add various robot models here. So in the layers, you can see various layers, like whatever. So this robot is basically have many links and joints. So all this robot is made from links and joints. So this robot, for describing this robot, you need to use URDF, which is known as Unified Robot Description Format. So which is basically XML format in which you define all the links and joints of the robot. So you use basically inertial, visual, and collision parameter here. So that will be covered later, like in more detailed video. So this is basically just the gist of what this URDF is. And you can also use SDF. So SDF is the language used by Gazebo, which is simulation description format. So that can also be used for defining a robot. So this, both are XML format with little different syntax of it. Yeah, that's about the describing the robot. In the top panel, you will see certain tools for moving your robot. Like you can pan your robot, you can zoom your robot, you can also add a few models like basic shapes you can add from the top toolbar. You can also adjust the light, the camera position, various views of the camera position. So that you can do here in the top panel. In the bottom panel, you will see various parameters like the RTF. So in simulator, you basically have something called as simulation time and a real time. The simulation time is the time in which your simulation thing is happening. So in real time is a time in which real time is ticking, like the real time that you have in a system. The simulation time, it may be that the same time can be faster or slower than the real time. So it's so RTF, this real time factor, is a ratio of simulation time and a real time. So it can be greater than 1 or less than 1. So you can adjust as per unit. So mostly your simulation runs slow. As you have very high computation application, it can be less than 1. So most of the time your simulation time will be less than 1. I mean the real simulation time will be less than 1 and RTF will be less than the RTF will be less than 1 and your simulation time can be equal to or less than real. Yeah, that was all about the real time factor. You can also play and pause your simulator as per your need. And yeah, that's the basic Gazebo UI. Next slide. So yeah, so you can use ROS Gazebo in various applications. So you can connect ROS with Gazebo. There is a package to connect that. So once you connect, you can operate various, you can read various topics. You can publish to various topics of the robot model. You can actuate various sensors. You can actuate various actuators, and you can take data from various sensors. So that's all about the Gazebo and ROS. So use of ROS and Gazebo at e-Yantra lab. So we use ROS and Gazebo for our various applications. We use for autonomous ground vehicle. We use for AUV, the drones. So in the left side, you see a drone. So this is the actual model of the drone that we have in the e-Yantra lab. So we use various ROS packages for it to do autonomous navigation and all. We also use it for the e-bot. So in the right side, you see is the e-bot, which is a actual robot hardware that we have in the e-Yantra lab. So we use the ROS packages, and so what we do is we first simulate whatever we need. So we can't directly put our script, whatever logic or script in the hardware. So first we create an actual environment where we want to have this robot to work. So we create an environment in the Gazebo simulator. We simulate the entire thing there, like whatever perception, actuation, whatever we need, we do that, and then we port it to the real hardware. So on the right side, you see is the mobile robot base with a UR5 robotic arm. So this was actually the robot model which was used for various applications. So we used it in the two of the themes last 2 years. So two of the EYRC themes last 2 years. So you can you must have seen few of the videos on the YouTube. So yeah, that was all the mobile base and a simulation of UGV. So we have done all the simulations of this in the Gazebo simulator, and then we have put it in the hard. So yeah, that's all about this. And we have some videos like last year we have created the exact replica of our greenhouse. So in Yantra we have a greenhouse. So in which theme was to make the robot like tomatoes, ripened tomatoes, detect ripened tomatoes and automatically plug and place it in the basket. And that was the e-by-RC theme last year. So this year also we have a similar kind of themes. So do participate so that you can get exposure of this theme. So yeah, we have video. It's not seen on the screen.
Visible now?
No.
What is visible?
The PDF.
Okay. I guess I have to
share the tab.
Share my screen again. Yeah. Give me a second. Okay.
So meanwhile, you can ask any questions you have, whatever questions you have. Any documentation for ROS with popular sim? Yeah, there is a documentation for ROS with popular sim. We have implemented similar thing 3 years back with ROS and popular sim. There is a course on Udemy for ROS.
I hope my screen is visible now.
Yeah, it's visible.
I'm not sure if this audio will be there, but let's see. Huh?
Yeah.
Audio is there?
No, it's not there. Okay, maybe that's fine. I can describe what's happening here.
Okay.
Okay, so this was one of the theme last year, named AgriBot, where robot has to detect the red tomatoes and pluck it. First, this theme was implemented in the simulator, the Gazebo simulator. So this was the simulator where the theme was implemented. The exact replica of a greenhouse was created with ripened tomatoes and so you see the robot has detected the tomatoes and it's trying to pluck it. Then it's trying to place it in the basket. So all this was autonomous. And here you see the real hardware. So this was a real hardware where students controlled it while they were sitting remotely. So last year, due to COVID, we were not allowed to have all the participants here at greenhouse. So all the participants were sitting at their home and they were controlling this board. So autonomous script was running from their side, and they were visualizing this through IP cameras. Yeah, that was these were the places from where participants. So that was all about the hardware from the simulation part. Yeah, there are a few questions. I will take a few questions. Many questions. Okay. Madhavar, is there a course on ROS? Yeah, there is a course on Udemy for ROS. Even we will be launching our MOOC soon, and in the e-Yantra competition, we will get the exposure of all the ROS. So we have detailed documentation of ROS in the e-Yantra competition and in ROS field.
Sir, ROS Wikipedia is sufficient to learn a ROS?
Yeah, that's sufficient. But only the issue is the documentation is not so straightforward. Like at the first time, you won't get all the things. So you need to read it multiple times.
Yeah. So I also want to comment on that. Like, there is documentation, but that is like you have to find some other resources apart from that given documentation on the wiki. So we are actually planning to create one MOOC on this ROS thing, ROS 1 and 2, and we will be releasing it soon actually from our side. So if you are really interested, so I guess all the content is already there, but someone need to channelize them and in some and to organize them. So we are thinking we'll organize it and we prepare video tutorials and a few assignments on that, and we put it in a MOOC format, and maybe we can release it to everyone so that anyone interested in ROS can take that MOOC and learn. So that's our plan actually on ROS. On ROS, like how we can actually pass this information to all our community. Yeah.
Next question is, do we have any things with ROS 2 this year? No, but in future we will be having ROS 2 book as well and themes. So can I run ROS on Windows? I would suggest no. You cannot run ROS 1 in Windows, but ROS 2 you can, but I would suggest no. But because if you are using Linux, that's a very good environment where you can get exposure of Linux, and also ROS, you can use it well in Linux. And also on MOOCs, please answer for that question. Is there any alternative for ROS? ROS is basically a very huge community out there. Like we have very huge number of packages, millions of packages has been built till now. Like most of the community, robotics of community uses ROS. So I would say there is no such huge community for any other any other tools out there. That's why I support ROS.
Yeah, actually, before ROS, people are developing their like in this sort of application, robotics. Uh, it's you can actually implement all sort of algorithm, but to integrate them is really a headache actually. So I would say like ROS is like a very good platform where you want to integrate everything to solve a complex problem. It's also depend upon your application that you want to build implement. If you say you want to just implement line following robot, then yes, you can also use some alternative. But when your problem is little complex, like actual robotics or I would say humanoid or self-driving car, then obviously you need some platform so that you can integrate more modules into your system. So at that particular level, ROS is really important, and I guess there is no other alternative right now, at least to handle all these scenarios. Yeah.
Yeah. Next question is, are there any themes completely based on embedded system and IoT this year?
Themes are based on embedded system, but I'm not sure if there is a theme specific to IoT. But all our themes are related to embedded system. That includes like the software and hardware part. And this year we have all the themes on hardware actually. But last few years, like due to this COVID and all, we weren't able to procure all the components and send it to participants. But this year, definitely all the themes are on hardware, which includes embedded system. But IoT, I don't think so. IoT related, especially like dedicated to IoT theme, is not there. Maybe we can think about this and we can plan if like uh, IoT, there is such demand of this IoT skills, and we can pack something related to IoT and deliver that as a theme. We'll think about this. Thank you for this question.
So, sir, are we like only on ROS right now, or we will be having firmware level development in the teams as well?
Yeah, we have. Yeah, there are. If I can release that, like how many themes we have, but we have number of themes, which includes other aspects as well, like the functional programming and microcontroller embedded programming and simple like the Python and all. Apart from this ROS and all, and there are also themes on specific to this ROS theme. So yes, we have other themes which includes the form on the side of developing algorithm at the firmware level and all.
Next is, do we need to know one programming language thoroughly to be able to take part in KYRC?
Not one programming language, I'm not sure, but you should explore other programming languages as well, because once you know a single programming language, like let's say Python or some C++, the logic is very important actually in the language. If you know one language, then you can easily learn other languages as well. So then it's about just the syntax and all. But I would say if you don't know any programming language yet, you can start with the Python and just focus on the logic building in the programming language. Just understand how you can handle the logic and all. And then in case you want to shift it to some other language, you can easily shift it because the logic is really important. Apart from that, it's I feel it's just the syntax if you want to switch to some other language.
Next question is there any ROS support for exoskeletons?
Yes, you in support. I'm not sure, but definitely you can design exoskeleton in the simulator, and you can use it because you just have to look it into the community, and someone will be working on this thing definitely, and you can take it further from that particular point.
Which Linux distro would be best for ROS?
Linux distro, all are best actually, but try to we normally use like एक step पीछे वाला, like right now 22 is running, so we use 20 or 18 because if I say like this 22, that will be still like on development side, so you can take one step uh, back and try to use that one.
I heard that there are many versions of ROS. Could you enlighten us about that? I mean, there is ROS
ROS,
Basic.
okay, you mean like Ubuntu and this Arch Linux and all this sort of?
Yes, yes, and similar to
Yeah,
that.
you can use
ROS
Ubuntu. You can use Ubuntu distro. Yeah.
Yeah, but ROS also has many types, right? I mean, which
There is dedicated like version for that particular Ubuntu version. So if you go for 20, then I guess it's Noetic or something, right? Right
okay,
side?
Yeah, it's noisy.
Yeah, yeah. But if you go to 18, then there is Melodic. So uh, like dedicated sort of ROS distro for dedicated Ubuntu version, like that.
Next question is, sir, what project do we need when I'm a beginner for ROS?
ROS, if you are a beginner, you can start with this TurtleSim, and then one Turtle board is there that includes simulation and Gazebo and all, and you can do some project called like Slam and all, like mapping and navigation. That is, I guess, the starting point. So you can import some turtle board in the simulator, and then you can generate environment in the simulator and just perform some Slam algorithm.
Next question is,
Yeah, Sahil, what is
yeah,
that?
I want to know
is it
more.
recommended to install Ubuntu by doing dual boot, or should I do it on a pen drive, or should I do it on virtual machine?
A virtual machine is not recommended because if you are running some simulation and all, that actually needs some core at CPU level. So you will face difficulty in virtual machine. I would suggest if you can dual boot, then it's a very good situation.
Dual
If
boot
you
will
can.
also split the RAM, right? Or
Yes, yes, you can split the RAM. Not the RAM, I don't know if you can split or not, but in virtual machine you can split the RAM. But if you are using the dual core, then the whole system will be used for that particular system, like which
okay,
is live. Yeah.
if Windows is sleeping, then Ubuntu will use the complete RAM, right?
Yes, yes, yes.
Okay.
That's why I'm recommending like doing the dual boot instead of like virtual machine.
Only the storage would be split, right? The RAM would.
Yeah, only the storage will be split. All the cores and the RAM you can utilize in dual boot.
Next question is, sir, I want to know more about the implementation of ROS code in actual project. Please suggest how can I do the same for my robo and IoT project.
Okay, what is the question again? I want to know more about implementation of ROS code. Please suggest how can I do the same for my robo and I application. You can do it. I'm not sure about like what sort of robo you have, but this the whole code is actually open source. You can go and check the actual source code of the package but what you are using, so you can go through the code, and in case you want to add some feature that is not suitable for your application, you want to remove or add something, you can make all those changes.
Next is, for drone simulation, can we use Gazebo? Yes, for
For
drone.
drone, yes, definitely you can use. We are using that actually.
Does there?
So last year there, over the last year there was one theme on a drone actually in
Yeah,
the
last year.
Gazebo itself. Yeah, that was strawberry staker or something, right?
Yes.
Yeah,
Yes.
strawberry
Also,
stacker theme was there. Yeah.
this following technical session also there will be drone technical session, so you can attend that to get more clarity on drone stuff.
When will be the drone technical session?
We will soon tell you the dates. It is not confirmed yet, but it will be on the month of August and September.
So all of the people attending here would get the email, right?
You will have to register at the link, so and you'll get the meeting link.
You have to register again, I guess, if I remember correctly, right?
Sir, in a EIRC,
Yes,
first of all, we have to complete the task in a software.
Sorry, can you repeat?
In a EYRC, first of all, we have to complete all the tasks in a software.
That totally depends on the theme you got, but yes, we recommend actually to first implement everything in the simulator, and then we provide the hardware actually, because it's better if we verify everything in the software, and then we can definitely put every code scenario we have on the hardware. So it's better to verify everything in the simulator. So yeah, so that's our approach as well. We first implement everything in the software or in the simulator, and once everything is like verified, then we switch to hardware.
Okay, just last two questions. Does there are mentorship provided for EYRC?
Does there are mentorship? Yes, it's so sort of like uh, I would say it's sort of mentorship only, because we design and divide task in such a way that and there are also in such a way that you can actually complete it, and if you have any questions, we are there at the discussion forum to answer the questions and all, and even we also conduct few live session to answer the question. But at the end, definitely it's a competition where you have to participate in competition as a like a competitor, right? So those concepts will be there, but yes, we try to provide as much information as possible, uh, not the solution but the knowledge. Yes.
Okay, just a last question. So where can we learn ROS 2 and is ROS 2 better?
uh, Again, for ROS 2 there is documentation available, but yeah, that documentation is, I guess, much worse than ROS 1. But yeah, there are few advantage of ROS 2 over ROS 1, but I would suggest this ROS 2 is still under development. It's better to first get a control in ROS 1, and then probably it will be easy to switch to ROS 2. We are planning to switch to ROS 2, but it's still in development and there are few bugs and all. So we are thinking, okay, let's stick to ROS 1 again, and maybe next year we'll start in the meantime it will be much better, I guess. Right now, in the given scenario, the concept and the fundamentals are much better, but the development it's still pending at like very regress level. It will be much better after maybe 1 or 2 years, but not yet, I guess. But the concept wise, yes, it's better.
Maybe we can take one last question and then we can start with the first. Yeah, one question is, any suggestions for DIY hardware kit for learning about drone development?
For drone.
Yes.
For drone, right? Yeah, actually, we are also developing few kits at our end so that we can actually pass, because as I mentioned, like we are planning some MOOC, right? We are planning those MOOCs on hardware actually, and for those hardware, we are developing some kit at our end so that we can pass those kit along with the MOOC to the participants, and they can have some hands-on experience on the hardware. And similarly for the drone as well, we are also designing few kits, uh, but the problem is it will be little costly. But yeah, in the simulation and all, it's possible to run the MOOC and to pass the information. But for hardware, we are in the process of developing all those kits. So once we have all those kits in our hand, we'll definitely uh, pass all those information on. we will normally open source all these, but we'll think about this. We'll have something at our end. Yes.